Okay, so in this video, we are going to see probability. So, what is probability? Probability is nothing but the mathematics behind random processes. So, let's say you take any process in the world, it will be either random or it will be a normal process. What do I mean by normal? Normal means like all the mathematics that you studied in school, all the physics laws, gravitation, electricity, magnetism, they are all normal processes. Meaning, let's say I'll give you an example. You take Earth and you see the rotation speed of Earth. So the Earth takes 24 hours to complete one whole rotation. So let's say on Monday you noticed Earth's rotation speed. It was 24 hours. It took 24 hours to complete one rotation. And Tuesday also it did the same thing. You keep observing the process, and the process will always be the output of the process will always be 24. It will not change. This kind of processes where you repeat the experiment and you get the same output are called deterministic processes. That is, if you take any ith observation, you can determine what its value will be. So these are normal processes. But random processes are, for example, let's take the usual ones, the coin tossing or the dice rolling. If you take these processes, let's say you roll a dice today and you roll a dice tomorrow, you roll a dice the next day, you keep repeating the experiment. You will never get three all the time. Three. This will never happen. So what in turn what actually happens is you get three, one day you get six, one day you get one. The output always changes, unlike normal processes. So as a result, these processes are called as random processes. So what is probability and why do we care? Now what probability does is it converts this random process into a normal process. And the reason why it's able to do that is because of the law of large numbers. So what is the law of large numbers? Let's clear it. So let's say, so we'll start with a story. So there are two people. One guy is called Ramu and the other guy is called Somu. So these are budding scientists, and they have an argument about probability. So what Ramu says is, he says you can't convert a random process into a normal process, and this is his reasoning. He says that let's take the coin example, and you toss the coin once. The experiment. This is the first attempt. You do it twice, a second time you do a third time, you keep tossing the coin, and you won't get heads all the time or tails all the time. So there is no way you can say that this process is normal. And what his argument is there are no patterns also in random processes. What do I mean? So let's assume that there is a pattern. Say you get heads, tails, heads, tails, heads, tails. Then Ramu is saying you can redefine the experiment definition as toss the coin three times and see the output at the third time. If you redefine the experiment as in this way, then if you conduct the experiment once, twice, thrice, then you will always be recording only this value, and therefore you will just get tail, and you can claim that this is a normal process. So only when there are patterns, if such patterns exist in this process, you can claim, you can redefine the experiment definition itself, and you can claim it is a random process, a normal process. Otherwise you can't do it. That's Ramu's claim. Now let's look at Somu's explanation or reasoning. So uh, so how does Somu actually makes it a normal process? So before we look into that, we need to understand approximation. Now, what is approximation? So let's say one guy earns $200 and another guy earns $956. Now, if I ask you between the two, who is richer, you will say this guy is richer because he earns more. But let's say now there are two people who earn 5 million and $200, and the other guy earns 5 million $956. Now, if I ask you who is richer, you will say no, they both earn the same, because in the significant digits they both are same, and only in the non-significant digits these digits are negligible. So since you already earn 5 million, this 209.56 is change money for you, so you can neglect it. So you can approximate both of them to 5 million, and you can say that they both earn the same. What this argument resembles is the Bill Gates argument. So one day Bill Gates was walking on the road, and $1 fell from his pocket. Now, will Bill Gates bend down and take the $1 from the ground, or will he just keep walking? So the why this question is interesting is, Bill Gates, in the 3 seconds that he spends bending down and taking the $1, in that amount of time he would have already earned $5,000 or something. So if he let go of this $1, he would have $4,999. If he picks it up, he will have $5,000. And if we use the approximation principle, practically there is no difference. So he can just let it go. So this is the approximation concept. Now, using this concept, we look into random processes. So this is how Somu redefines the experiment. He says the experiment is defined as tossing the coin 100,000 times. Just imagine a very big number here. So what he means is basically, and he claims this experiment is a normal process. So let's try it. So doing this experiment once is tossing the coin 100,000 times and capturing the result. Let's say we capture the result, and this is a table. It says how many tails are there and how many heads are there. These are complementary. So tails plus heads is 100,000 only. So if we capture only this value, essentially we have captured how many heads are there also. So let's say you did the experiment once and you got some 50,963 tails, and you do it second time, you get 50,265. You do it third time, you get 49,966. You keep repeating the experiment. Now if you look at these numbers, and if you plot them in the number line, so this is 0 and this is 50,000, and each point, each eye, if you plot it, it will lie here somewhere. So in one window all of these numbers will lie. So what this means is you will never get some number that is here or here. So the maximum number of heads, or in this case tails, that you will get is 100,000. So how many ever times you conduct this experiment, all those values will always lie in a short window near 50,000. It will never be 1,000, that you get only 1,000 head tails and you get 99,000 heads. It just never happens. So, and if you approximate each number, it will turn out to be 50,000. So what happens is, so if you approximate this number till 3 digits, it will become 50,000. This number 3 digits, it will become 50,000. So what happens is, you conduct the experiment, and each time by approximating you get the same number. So now it turns into a normal process. So what did Somu do? What he did is, let's say you toss the coin once, you toss the coin twice, you keep tossing the coin. Now this is a random process because each time it's different. But Somu claims you can make groups. You can say all these tosses are one experiment. This is one experiment. And similarly, if let's say some 500 tosses are one experiment, the other 500 is another experiment. So this way, if you keep grouping them and if you count the number of heads at each experiment, these numbers will lie in a small window in the number line. And if the group size is bigger, the window will become shorter. So let's say this window size is epsilon. As the group size is 500 or 500,000 or 5 billion or million, as you keep increasing the group sizes and you compare those big groups, then the difference in numbers will become smaller and smaller. And this is useful to us because as it becomes small and small, you can approximate them and you can say, oh, they all are same. So this is the law of large numbers. That is, when the experiment size in a random process, if the grouping size, let's say you keep conducting the experiment and you say 100,000 is my group. In such groups, approximation is easier to do because the difference in numbers, the epsilon, keeps reducing and reducing. So as n tends to infinity, epsilon tends to 0, and you can approximate them as the same number. So this is the concept of probability. So when somebody comes and tells you that the probability of getting a head is 1 by 2, it means that if you conduct the experiment of tossing the coin these many times, then exactly by 2 of these will be heads and by 2 of these will be tails. Of course, by doing approximation, and as you keep increasing the number of zeros here, as you put a bigger and bigger number and plug into this equation, the more accurate your answer will be. So if you just take 10 tosses and if you say you will get 5 heads, that is really wrong. In 10, this probability equation fails, but in 100,000 something, this huge number, it succeeds. This is the concept of law of large numbers. And there's one more thing that you need to understand here. The another thing is, so if I take a small sample and if I say 1 by 2 of them, say 10 times I toss the coin and I say 5 times I'll get tails, this is wrong. Like many times I'll be very wrong. But if I take a huge sample and if I say half of it will be heads, I'll be right, because I'll be more close to the answer because the window is small. Now if you see here, I'll be wrong, I'm saying. So let's take a case where I am wrong. Let's say I got 9 heads and 1 tail, and I'm saying law of large numbers works. So if after 10 tosses, if I keep tossing the coins, so right now there are 9 heads, the bar is high for heads, and there is 1 tail, small bar. But if I keep tossing, both bars will grow, and they will grow to become of equal sizes. Negligibly, there will be small negligible difference between them, epsilon. This is what law of large numbers claims. So for this picture to turn into this picture, obviously there should be more tails coming than heads so that they become equal, right? This is called as the gambler's fallacy. So just because you got lots and lots of heads and less number of tails, your belief is that in the future tosses, you will receive more tails than heads. So your probability or your belief in the percentage of heads in the percentage of tails increases. You will say tails is more likely to come because the trend in a huge sample space is half of. So to become half of, this guy needs to grow. So there'll be more tails than heads. If you say that, you'll be wrong. I will tell you why you'll be wrong. Because one way to look at it is, let's say you have tossed the coin some 10 million times. Okay, the 10 million plus one time that you toss the coin, the probability of getting the head is still half, because the coin does not know that it has produced these many heads and these many tails, and the coin does not know that the law of large numbers should be agreed, so I should give tails more. The coin is unaware of the history of the previous tosses. That is one way to think about it. But then how will law of large numbers work? How will this equal to this? The reason is, since from 10 you are going to 100,000, the change, the transition will be unnoticeable. It will not be very obviously tails won't grow. So as you take many the snapshots in between, it is not like the picture will grow, it will change like this. It will be like this. Next picture will be like it's growing. Next picture will be like it is growing. And you won't see this trend. Instead, what you will see is minute differences. So this is what you will see. It will be big, and the next picture it will grow, and this will grow negligibly. You won't notice the difference, but slowly this will catch up. But it will not catch up in a in such an obvious way that you will think, such an obvious way. The change won't be so obvious that you will say that, oh, you see, we are getting more tails than heads. Just to satisfy with the law of large numbers, this coin is producing more tails. That will never happen. And the assumption and the belief that that will happen is what is known as gambler's fallacy. So what is probability? Probability is nothing but you take a random process and it will have these many. Let's say, I'll give you an interesting example. You take a girlfriend and you see what dress she is wearing each day. You know in her closet that she has only red dress, green dress, and blue dress, and you keep observing her. She wore red, she wore green, she had red, blue. It is all random. But as Somu said, if you take bigger and bigger groups and you compare the results of those groups, so it will be like two. Let's say in 1,000 tribes, uh, 200 reds you get a table. First experiment, 200 greens you get, 200 blues you, oh wait 200 400 600 blues you get. And the second time you notice, second set of 1,000 days you notice, you will see that there will be change, but it will be negligible. 196, 220, and this will be the whatever the remaining is. And as the sample space, the grouping, if you take a bigger and bigger grouping, the change in the numbers, the window, if you plot these numbers in a number line, say this is 200 and the numbers are lying here, this window will become smaller and smaller, and your approximation will be more and more accurate. And you can claim that if you take a sample space of 1 million something, how you will say probability is, you take the sample space and you see the occurrences. So let's define probability now. You take a huge sample space and you count how many greens you get, G1, how many blues you get, B1, how many reds you get, R1, and probability will be R1 by S, B1 by S, A1 by S. So if you take a even bigger sample, 2S, in 2S how many greens I'll get is, you just multiply. So in S, if I get A, then in 2S I'll be getting 2A. So it's like probability will work. So whatever, so when somebody gives you a probability, for example in heads or tails, if they say the probability is half, then if you Get a huge sample, then in that sample, half of it will be heads, half of it will be tails. If you get a smaller and smaller sample, this equation, this probability will start failing. And this is the concept that I want to drive home. In future videos, we'll dive deeper into probability. We'll see joint probability, conditional probability, we'll see Bayes theorem, and lots of things. Thank you for watching.